Yeah, I have it. Something.
All right, beautiful.
Hello, this is the Embedded Security and Hardware Hacking course at BWSI. We leverage deep relationships with security engineers in industry and a project-centered curriculum to introduce students to the unique challenges of securing the world of embedded systems. From facing software-based exploits to physical hardware-based attacks, students will learn how to defend the critical computing systems of tomorrow from future threats. Our students compete to design a secure embedded system using the lessons they learned throughout the
Everyone
course
else?
about embedded software engineering, cryptography, side channel
Isabella,
analysis, fault
can you make
injection,
sure
and
they all
more.
know we're starting?
Then they put their designs to the test by penetration testing other teams
Yeah, you
in
can
order
hear
to
me.
capture flags. The teams with the most secure
Good to go.
designs
Okay. Hi,
or the
everyone. My
most
name is
creative
Madeline
attacks
Esty. I'm
will
the lead
prevail.
instructor for the
Happy
Embedded
hacking!
Security and Hardware Hacking course. Sophia DeClean and Ted Clifford, who also work at MITRE, were also instrumental instructors in this course. We also had a fantastic group of guest lecturers from MITRE come in throughout the course to give students lectures on EMFI, fault injection, differential power analysis, and a whole host of topics like that. We also have our wonderful TAs that are behind the camera that I'd like to acknowledge. We have Billy, Charles, and Isabella. So thank you to all of the course staff for making this course possible. So the students have been hard at work for the last 4 weeks, and specifically starting in week 2, students started to work towards what we call the course design challenge. And for the design challenge, students were tasked with the dilemma that a car company needs a way to securely send firmware updates to your device, to your car. And students implemented this functionality as a bootloader, which they programmed to run on a Tiva microcontroller. And so, in real life, a car company might need to do this to fix bugs, to update your car software. So it's a very realistic scenario that students had to implement on a smaller level. And so today you'll see presentations from all 6 teams that we divided our course class up into, and they each were tasked with not only designing and implementing this secure system, but towards the end of the course, they were given access to other student designs so that they could try and hack into them and exploit any security vulnerabilities. So without further ado, I will hand it off to our first team to give a little bit more information on what the course project was, as well as their design and attack phase. So thank you. Okay.
All right. Thank you, Maddie, for the introduction. So to go more in depth for the competition, we have our factory that produces cars, the hardware, firmware, and the actual car that the end user utilizes. And again, the hardware is the Tiva microcontroller. The goal here is to maintain a secure transport layer between the factory and the car, as well as securing the car itself from attackers that are using the car alone. And in order to maintain this security, we have to do these 4 following things. So we must keep the encryption keys that we use for the firmware secret, because otherwise attackers who control the car or use the car would be able to control it arbitrarily, like turn off your cruise control or do other things that aren't generally good for car companies. We also have to prove who made the firmware, so people can't put malicious firmware on the car and again control it to their own wants. And also another factor is refusing old versions. Say we make a fix on the car's firmware, and we don't want an attacker just to be able to undo that fix by switching back to an older version. And lastly, we want to keep the car up and running always. Otherwise, your car just becomes an aesthetic piece, which we don't want.
Hi guys, my name is Torox. Jason?
Hitachi.
I'm Brian. Our team name is the BWSI, and now we're going to give you a quick overview of our bootloader that uploads the firmware onto the car.
So in terms of the update process itself, to get your car working, we have 4 steps that also everybody else has, but we have some unique aspects as well. We build the bootloader first with the public-private key encryption system, and we write that into where our flash storage would be. Once we have the raw firmware built from our code base to get the car functional, we encrypt the firmware so attackers can't just read our source code and analyze vulnerabilities as an extra layer of security. And we also sign the firmware and bootloader itself to ensure that everything that's being transmitted to the car, all the raw data, is indeed coming from us, the factory.
Yeah, and so the next step is the firmware update, which first sends a 98-byte header, and then packets of 256 bytes to ensure like the buffer doesn't overload. And it holds no key, ensuring security because the file is already encrypted and signed. And then next, the final step is the bootloader, which verifies the signature and refuses any old versions, meaning it'll only take in the current version. And it keeps a firmware backup just in case. And then it tests the keys twice to prevent any fault injections. And the car and the communication is hostile, so the bootloader can't inherently trust anything.
Um, so this is how the update is protected. First, we'll start off with the label. This will include its version and size. It'll be about 6 bytes, so it'll provide information about how big the file is going to be sent. And then we'll supply a one-time number, which will make it so every package that is sent to the device is different. That'll be 12 bytes, so we'll want to ensure everything's changed. There'll be a tamper seal, which will catch any edited byte. So if an attacker tried to change any information that was being sent, then the tamper seal will, stop that and catch it. That'll be 16 bytes. And then lastly, for the final information, there'll be a signature, which will prove that, the secure factory, which is us, that we made it. And then we'll have the contents. Finally, they'll be sent, as stated before, in packets of 256. And then the label is plain text, so we'll be able to easily seal in signature. If any byte is edited, absolute any of them, the seal instantly becomes invalid, and then nothing else will be able to be read without the valid key.
Okay, so because we don't want just anyone to update our car firmware, we need to add a signature so that it can be authenticated. Additionally, we're sending our packages in like a mail, which basically means that it's not only encrypted, it has a signature, and also we can tell if anyone's ever opened it before. On the more public side of things, which is on the chip, we have an authentication key, which actually verifies that the package is where it says it's from. And we also have our decryption key living on the chip, which although attackers can see, it's been scrambled. And so when the encrypted package actually comes, we can unscramble it, use the decryption, and then completely wipe it so that it can't be used again. What this entire thing means is that basically if someone was able to copy our chip off, they wouldn't even be able to replicate our package or be able to forge anything.
So for our new software, we put it in a side room first, where we read the label and check the signature, and then we park it and scramble it in a side room. And then the car keeps running as the old copy boots up.
All right, so after we confirmed the signature, we rebuilt the key in order to be able to decrypt the ciphertext, and we also have to confirm the poly 1305 tag to ensure one last time that it is an authentic build. And after that, we install and stamp the version to continue with the firmware update. Okay, so here are some of like our security provisioning. Okay, quickly. Okay, provisioning updates to the car. So in order to make sure that the car doesn't roll back to an earlier version, we have to ensure that the update is of a later version than before, and we also ensure that like interruption doesn't break the firmware and doesn't cause the car to malfunction, and we mark each update that is previously set in.
Okay, so one of our favorite attacks that we did on another team was basically a hardware timing fault, and we do this by resetting the microcontroller a bunch of times in order for it to skip the check to see if the firmware is valid. And a fun fact is that we were the only team that got a flag from another team.
And yeah, there have been 988 failed attempts to break our firmware, and 0 of 5 flags indicating vulnerabilities were taken from our provisional board. And yeah, thank you guys for listening.
Alrighty, so we have time for just one question. So to the Byte of 87, you mentioned that you check keys multiple times on the bootloader, but can you explain why?
Yes, so this is to protect against what are various forms of attacks known as fault injections. an example that we have for our favorite attack is that by controlling when the microcontroller has power, we are able to control the individual instructions in code that are executed. And by doing it in a precise manner after the microcontroller boots, we can skip instructions. In order to prevent this, you can simply check that the keys or the firmware is valid multiple times. And in doing so, it makes it incredibly difficult for the attacker to rely on luck to control that timing cut, which is why we check the keys multiple times.
All right. Yes. So we'll head on to our second team, but also just a quick note for everyone that's in person. After we get done with the filming portion, we'll have the opportunity for you all to go around to each individual team in case you're not able to hear in the back currently. So just wanted to make a note of that. Thank you. All right, hand off to Beaver 5.
Hello, everyone. We're Beaver 5, and this is our final, and the members of our team include...
Hi, I'm Millen.
Hi, I'm Claire Scheinbaum.
Hello, I'm Andrew.
Hi, I'm Margaret.
Hi, I'm Claire. Okay, so the first thing we want to talk about is our use of AES GCM. This is the main security protocol we use in our firmware bootloader. This provides confidentiality, integrity, and authenticity, all of the CIA. AES encrypts the firmware using a secret key so that people can't read, or attackers can't read what is in our program. Then GCM generates an authentication tag over the ciphertext and metadata. So if anything is altered, the firmware will detect that and it will reject the update. Then the version number and release message will remain readable, but cannot be modified without invalidating the tag. And then our message protocol and frame format is that our firmware protocol gets securely transferred from the PC to the microcontroller. And the package that was sent contains the version, metadata, IV, authentication tag, and of course the encrypted firmware. And it is sent over UART in small frames, which are 16 bytes. Then the AES GCM tag will verify its identity, so any modified or reordered data causes the update to be rejected.
Okay, so for how our bootloader handles everything, upon installing the bootloader, we disable all of the hardware ports to do debug and flashing. So that essentially bricks the board so that nothing new can be uploaded without going through the bootloader. And then when receiving a firmware update, it'll check the signature using the keys it has. And then if it matches, then it'll approve the firmware. And if it doesn't, then it'll reject it.
All right. BLbuild.py is the Python script that builds all of the bootloader into a binary file that is flashed onto the chip and creates the AES GCM key as well. That's used for encrypting the firmware and authenticating future updates. Then moving on, we have firmwareprotect.py, which actually uses a key that's taken from the bootloader, the secret build that's outputted from the past Python script and generates the authentication key and makes sure that all of the firmware that comes from future updates are legitimate and come from the actual factory rather than another place.
So for firmware update.py, we read the blob provided by the fwprotect.py, which contains 3 sections. The sections is the header, the ciphertext, which is the firmware, and the ASGCM tag. And we send this over the serial in that order. And the ciphertext is specifically sent in 16-byte chunks with a 2-byte length specifier. And once the GCM tag is sent, that very last OK message confirms that the update succeeded. So for each flag, this is how we protect it against them. For rollback, we don't want the attacker to install older versions of our firmware. So what we did was we binded the version with the header, and we also compared the version so that the attacker can't upload an older version. For invalid and malicious firmware, we don't want an attacker to obviously upload any malicious firmware or invalid firmware. So what we did was we verified the firmware uploaded with an AES GCM tag. For intellectual property, we don't want attackers to be able to read our firmware. So what we did is we encrypted the firmware with AES GCM. And then finally, for memory read, an attacker can easily dump memory using the debug port. So in our code, we disabled that port.
So an attack that we tried, we noticed that there was a software lock on one of the Tivas that we're attacking instead of a hardware lock. And so what we could do was exploit this by resetting the board, and there would be a short window where we could establish a connection and then dump the flash. And so we ran a script that would constantly try to establish this connection and then kept on resetting the board to try to connect.
We have come such a far way since the beginning of this program, and in reflection, we've achieved a lot. One of the things that we achieved on this project was that we were able to successfully secure the CIA triad through AES-GCM. We were able to prevent older firmware from being installed. We were able to verify firmware before it runs, and we were also able to prevent firmware readout. Also, in reflection, if we were to do this program again, or if we had more time, what we would do is we would use different encryption keys on each device and also add signing key rotation. Thank you.
Thank you.
All right, so our question for Beaver 5 is, what is a vulnerability in your own design that you discovered that you are proud of discovering?
So, vulnerability we're proud of discovering is the JTAG and lock that we just talked about earlier. So, as I mentioned, some teams used a software lock, and then we found out that like we needed to permanently use boot config to permanently disable the ports, and so this would prevent a hardware lock that would force anyone trying to use debug to completely wipe the board before being able to use it again.
Okay, we'll move on to our next team. The null pointers. And make sure to speak up a little bit.
Hello, we are the Null Pointers. I'm Timothy.
I'm Nandini.
I'm Arav.
I'm Nina.
I'm Adit.
And we're here to talk about our final project, the design, and the some attacks we tried. So we're going to start off with one of the Python scripts we used.
So the first Python script we use is called BL-build. What this does is it compiles the bootloader and it generates our random keys in that it generates our cha-cha-20 poly 1305 key, which was our encryption algorithm, and it generates the public and private keys for ED25519, which we use to verify that the firmwares came from us and not from a different team trying to attack our firmware. So it compiles both of those into the bootloader, and it also compiles both of those into secret build output.txt.
Okay, so the second Python script that we utilized was fwprotect.py, which packages and protects our initial firmware. Basically, it parses the secret build output.txt and it takes out the cha-cha-20 poly 1305 encryption key and the ED25519 private key in order to encrypt our version number, message, and firmware, and sign our entire package, including the magic, the metadata, including the message length, firmware length, and cha-cha-20 nonce, and including the poly 1305 tag. So our third Python tool was fwupdate. Here, this tool would send 256 byte chunks over UART to the bootloader. After each chunk was sent, the bootloader sent a confirmation byte. Once all of the data is sent, then the update tool prints a confirmation message saying that the update was successful.
And so for our communication protocol, how we're transferring the data, we use UART, which is a method of transmitting data bit by bit, and there's no shared clock signal between the sender and the receiver. This lack of shared clock signal makes it very difficult for a timing side channel attack to be used against us, which is why we chose this method. We break the data into chunks 256 bytes as opposed to a smaller value because it's faster.
So this is the bootloader load functionality. Here, after the data is sent by fwupdate, the package is reassembled. Then we verify the ED25519 signature against the public key stored in bootloader. After this, we decrypt the version number and message. We reject any older version numbers, except for version number 0. After this, we decrypt the cha-cha-20 symmetric private key signing algorithm, encryption algorithm, and then we authenticate the poly 1305 tag. If any of these checks fail, then we clear flash memory and send a reject byte back to the update tool.
So for the bootloader boot function, so after it verifies the installed firmware using cha-cha-20 poly 1305 and the signature ED25519, it's going to check whether the firmware is going to be valid or not. If it is valid, it jumps the firmware to the start address and passes the execution onto the firmware. Otherwise, the bootloader will end up printing a rejection message and wait for a future update.
Okay, so to summarize our overall design flow, BL-build will generate our encryption and signing keys, and then the cha-cha-20 poly 1305 key will and the ED25519 public key will be compiled into bootloader.bin and flashed to the TIVA board. And then our CHA-20 poly 1305 key along with our ED25519 private key will be parsed by FW Protect in order to encrypt and package our initial firmware. That initial firmware will then be sent to FW Update, which will be sent to bootloader.c, which will either accept or reject the firmware. If the firmware is accepted, it will be flashed onto the TIVA, and if it's rejected, it will send a reject byte back to FW Update, and it will erase the flash memory.
So some of our favorite attacks that we tried to carry out on other teams, our first one was electromagnetic fault injection, or EMFI. So we use a machine called a Pico EMP, which uses pulses to send electrical signals to the microcontroller at specific times. And what we can do with this is if there's an instruction that we'd like to skip on the microcontroller, such as a check for the version, we can send a pulse at that specific time to skip that check and flash an older version and get one of the flags.
Another one of our attack strategies we tried was differential power analysis, which is a side channel attack to try to measure the amount of power being consumed by the victim board. And what this does is you can try to find patterns to see if you can identify bytes of a key for AES.
And the final attack strategy that we implemented was attempting to reset the chip during the flash erase window using a pirate bus and connecting it to our TIVA board. And if we're able to reset it before the new version is written into flash memory, then we're able to flash an older version. Thank you so much for listening to our presentation.
So a lot of teams for this design challenge chose to use AES, but this team chose to use a different cipher. Can you all explain to me why you chose to do this cipher?
So the reason we chose a more unconventional cipher algorithm was because, first of all, since it's different than other teams, it would be harder for other teams to break into it because it's unfamiliar to them. And second, the algorithm we used is faster than AES on the TIVA board, and it's also more it's as secure as a more secure variant of AES while still having the speed of the less secure variant. And then it also it has built-in authentication and integrity checks as well. So we have double checks on basically everything there.
Thank you guys. All right, now moving on to our next team.
Hello everyone, we are Team Non-Volatile Memory and this is our design challenge. My name is Heymonth.
I'm Arnab.
I'm Krish.
I'm Sean.
And I'm Kavi.
So the first thing that happens when we run our code is BL build, and that builds the bootloader. And additionally, it also will generate a random AES 128-bit key at build time. And we're using AES GCM, which also adds a signature using the same key. And since it's 128 bits, that key is unbreakable through brute force. And then that key is stored in the chip and it's not available to attackers.
The next script we're using is the firmware protect.py, which essentially is a script that uses 3 goals to bundle it into a secure package to protect confidentiality and integrity and authentication. So the first thing it does is it reads the AES 128 key, which is converted from the BL-build.py, and then it turns that into an updated bundle using the header, the nonce, and version notes or version number and the release notes, so that even if an attacker intercepts the updated package, it's turned into ciphertext, so it's unable to be read by the attacker. Next thing is that protects confidentiality. So since the fact that it's converted into AES GCM, like Arnab mentioned, when an attacker reads it, people are not going to be able to read the contents of that file. And what AES GCM does is basically behaves as a stream cipher, which creates a GMAC tag for every type of loop, which means that it protects the integrity over it. Oh, sorry. This is the flowchart for firmware protect.py, which essentially goes through how, in order, what components are being utilized.
Moving on to the firmware update tool we used. So this tool is primarily used to transfer the firmware to the bootloader. So first it would take the firmware protected bin file and it would send that over UART. And to make this transfer more manageable, it would split the firmware into frames, which went up to 255 byte chunks. Each frame would have a start byte, a length field, and the firmware data itself. Once the frames were all sent, it would wait for the bootloader to acknowledge it before continuing to ensure reliable communication. And then once all of the firmware is sent, it would then wait for the bootloader to verify the update and return the final output, which basically means it would wait whether it should update or not. And one important note is that the firmware update tool isn't used for security. It just used to deliver the firmware to the bootloader.
So lastly, we have the bootloader. The bootloader itself has two modes, an update mode and a boot mode. So for update modes, it'll receive packets from fwupdate.py. It'll process them and store them in a separate field for firmware that's to be staged, and it's going to keep doing that until it receives all the bytes. After it's received all the bytes, it's going to verify the AES GCM tag. If the tag check passes, it's going to set a flag in memory, and then it's going to go to the boot phase. If it fails, it's going to erase all the encrypted firmware it wrote. Then for the boot phase, it's going to check if it needs to update. If it needs to update, it's going to start decrypting all the firmware to the boot area, and then it's going to boot the firmware. If the flag is not set, it's just going to boot.
Okay, so now we will go on to our attacks. So we used a lot of attacks, but the two coolest ones we used was the fault injection and the DPA. So we use Pico EMP for fault injection, and how that works exactly is there's an electromagnetic pulse that is sent to the chip, and based on that, you could bypass certain areas of code. For example, you might be able to bypass a password to get straight into the system. Then we also use DPA, and this basically measured the tiny variations in power consumption while running cryptographic processes. So then we could directly get keys based on this. Okay, thank you.
Alrighty, so our question for this team is how did you balance managing confidentiality, integrity, and authenticity even though you didn't use a signing algorithm?
So one of the most important things in a car bootloader is we want to make sure you're not running malicious or invalid firmware. So we don't care as much about confidentiality as we do about integrity and authentication. So that's why we used AES, and we would, in a real scenario, we would provision one AES key to each car. That way, if one car gets hacked, they can't hack the rest of the cars. And in a more secure implementation, we would also use a signing algorithm. But our primary goal is integrity and authentication. We don't care as much about confidentiality in the real scenario.
Thank you. All right, we're gonna move over here. Awesome, and we have two more team presentations before everyone can go around kind of science fair style to all of the teams in person. Thank you. I will hand it off to our next team, the TIVA Task Force. And speak up.
Hey everyone, we're the TIVA Task Force. I'm Michael.
I'm Stefano.
I'm Austin.
I'm Sylvie. And I'm Aditi.
So the basis of this challenge was we had to create a secure bootloader, which was able to successfully install and boot firmware and protect it from any malicious attackers. And so our goal was to design some bootloader.c file and helper Python files such that we can provide confidentiality, integrity, and authenticity to our program. So the first Python tool we used was called blbuild.py. And so this had a few functions. The first one was to call make for the bootloader. And this would compile the bootloader.c file into a bootloader.bin file, so a binary file, which would get flashed onto the TIVA. The next was to generate secret cryptographic information we would use to protect firmware. And so we used a cryptographic pseudo-random number generator here and stored the secrets in a file called secretbuildoutput.txt and a header file called secrets.h.
So we used fwprotect.py to turn the raw firmware into a protected package. We decided to use AES GCM. AES is a symmetric block cipher that would provide confidentiality by encrypting our firmware. And then we used GCM, which would create an authentication tag, which would be checked by the bootloader to make sure that nobody tampered with our data.
Our third and final Python tool was firmware update.py. And what this did is it took our protected binaries and it allowed us to provision new boards and to update boards from older versions to newer versions or back to debug versions. And what this firmware update.py tool did was it did not use any of the cryptographic information, as that was all handled by the bootloader.c that was already on the TIVAs. And that file that allowed us to check the signature, integrity, and versioning for the firmwares.
All right, so now on to our next we're talking about our bootloader now, which is a module that basically controls and manages all the firmware that's on the board. And basically, it can be simplified down into two different functions, which are boot and update. And what boot does is it executes the firmware that's currently loaded on the flash memory of the TIVA and displays the release message associated with it. And update receives the update command and receives the firmware package in specific chunks, and then it writes those after specific confirmation checks to the TIVA's flash memory, one page at a time. As mentioned before, we implement security features, and we decrypt the encrypted firmware using AES GCM, which is authenticated by the GCM tag. And the tag also includes metadata in additional authenticated data like firmware size or version. And we also implement specific timing protections against side channel attacks related to timing. For example, we use bitwise operations that run constant time for comparisons, and we also implement randomized delays.
So talking a little bit about memory protection, we use EEPROM. This is a non-volatile memory program. So this means that data is safe even when the program turns off. So we employed EEPROM for two different reasons. Our first use was it stored our installed firmware. So this means that if a user was trying to upload it with an old firmware version or the current one, we would reject that and we would only accept new updates. The second use was a failed update counter. This drives our back off delay. This means that if a malicious user was trying to update the system continuously in like a brute force attack or a side channel analysis attack, specifically DPA, the user would have to wait in between each try, especially as they failed more attempts.
Something we also wanted to protect was the flash memory. So JTAG pins are used for programming flash memory and code debugging. So that would provide direct access to the flash memory. So we wanted to convert that to GPIO pins, which are used just generally. So we included a function called reallocate JTAG to GPIO in our bootloader C file, which would protect our flash memory from being read. Yeah.
So a few challenges we ran into. The first one was what Aditi was talking about converting our JTAG to GPIO pins. The issue with this is it bricked our TIVA board a lot, and there was at a point where all of our TIVA boards were bricked, and we had to reset that, but we didn't have the software for that. Another issue was reading the memory properly. Because of the SRAM limitations, we had to do 1 kilobyte page at a time rather than buffering the entire firmware package in one go. And another issue, we were all on different operating systems. Some of us were on Mac, some of us were on VMs, and some of us were on Windows, so it was different operating that. So looking into the attacks, we were very excited to explore in the attacking phase. Since we knew all the competing teams had really great software algorithms and schemes, we looked for the more hardware side of this. So the first one we talk about is DPA. This is a side channel analysis attack using an oscilloscope to use the power traces to actually discover an AES encryption key. Another one was EMFI, which stands for electromagnetic fault induction. This uses very focused electromagnetic signals to actually like break a chipboard, not invasively, so it doesn't actually damage the board, but it glitches it so that you can do things like skip an instruction. So you can skip a authentication instruction, and therefore you can store invalid firmware. So that's all. Thank you, thank you, thank you.
Awesome. Okay, thank you to the TIVA Task Force. Our question for them is, can you tell us a little bit more about the differential power analysis and what you considered for attacks?
Yeah, so talking a little bit about what DPA actually is, basically what it says is that you can use the power traces to leak information about the encryption key. So you can sort of split this up into two procedures. The first procedure is running a system's code multiple times and XORing it with different bytes, and also using the Hemming key to find out all the different possibilities and run those power traces and record that over time. The second stage is using those power traces and then analyzing that to find the correlations and the specific marks in it to actually find where the traces could be and the specific bytes over each thing. So through that, you can find the AES encryption key.
Thank you guys. All right, and we're moving on to our last and final team. We're gonna come over here. Great. Perfect. If people could push back just a little bit so our presenters have room, thank you. All right, get wrecked. I will turn it over to you all.
Hello, everyone. We are the team Get Wrecked. I am Catherine Burkhart.
My name's Alice.
I'm Henry.
I'm RJ.
And I'm Derek.
Okay, so starting with our secure design, we had Python tools and we had 3. So for instance, we had blbuild.py, we had fwprotect.py, and fwupdate. So in blbuild, we generated the keys, and essentially, so as you can see by the diagram, some get sent to bootloader.c. And here, then they're embedded into the binary file of bootloader. And then the AES key is sent to fwprotect, and here it encrypts the firmware with AES GCM. And then the version and length is prepended to this, and then the entire package is signed with an ECDSA signature. Then in a firmware update.py, we have the secure firmware goes through a version check, and essentially this prevents rollbacks. And then it is sent over a UART serial connection, where then it is chunked and sent, and each chunk is also confirmed each time. And essentially, this makes sure that there's nothing tampered with, and the bootloader can reassemble all of the frames.
All right, so next I will be talking about the encrypted firmware bundle diagram that we have here. So with this diagram, this is basically a visual representation of how our information gets sent over. So as you can see, there are 2 main portions of our firmware. So we have our encrypted bundle data in red over here, which as you can see, it's red encrypted. And we also have our unencrypted header over here. So we have different aspects of this header, and along with the bundle data, we have 2 versions over here to make sure that if there's any modifications, they can be checked against each other to prevent rollback attacks. We have our link to make sure that there's nothing that's been added on. Our IV, our tag, again, is there for extra security to make sure that no modification has been made.
So in the factory, we will be powering on the TIVA for the first time, initializing all the peripherals. So this is the GPIO pins, UART connection, and we're checking our magic, which basically locks the debug and doesn't allow any communication besides over UART.
If the magic returns a false, we will attempt to lock our debug and then we check if our keys are provisioned. If they're not, we will write our keys to EEPROM and also the version number, which would be 0. And then erase the keys from flash to ensure that there's no way for an attacker to read it. If at any point in these steps it will turn an error, if there's an error, it will restart. Yeah. Okay. Then after the startup sequence, we will wait for a UART signal from the FW update or a user. If we receive a U, we will head into the update mode. And in the update mode, we will receive the 96-byte header. If this header is valid, we will then check the ECDSA signature, and if that's valid, we will decrypt. If that fully works, we will then check our GCM tag. If at any point it returns an invalid, we will then return an error and reset. After checking the GCM tag, we'll write our firmware to flash and then update the version number.
After all of this, if we receive a B from over the UART signal, it'll go into boot mode, which checks if using secure boot, which checks a firmware hash. If it's not valid, it'll reset the board and you have to re-upload a valid firmware. If it is, it'll lock flash to read only, it'll read the vector table, and then it'll check if it's a valid address. If it's not, it'll reset, and then again, you have to re-update it. And if it is a valid address, you have to boot the firmware.
Right, so now onto some attacks that we did.
One of my personal favorite attacks that we did is called a supply chain attack. What this attack does is it targets the device before it actually goes to the main factory where it gets provisioned. So you can see in this kind of sourcing area. Unfortunately, after we developed it, this attack was deemed out of scope, so we weren't able to use it, but I still think it's very interesting. The main part of this attack is carried out by a utility I wrote called supplychain.c, which has a lot of things it can do, but the most important one for this is this lock boot config option. The boot config register is what's called a bootstrapping register, so as soon as the microcontroller boots up, it first checks that register and then determines what to do. Normally it'll boot to flash, but if we can change this one value to look for a GPIO pin to a certain value, we can then boot into the ROM bootloader instead and have a whole backdoor access into the system. Then after we set that, we can self-destruct it, which will basically wipe the flash. There'll be no trace of it. Take it to your unsuspecting TAs who will then flash it with the firmware. And then on the very next boot, you can connect a jumper between those GPIO pins. And then when it boots up, it'll enter this ROM bootloader mode where I just have a Python script that can then communicate over serial instead of the locked debug interface. And then take whatever payload binary you want and stream it directly into the chip. And this bypasses all the security features because we're booted up in a specific way. This payload binary can be basically anything, but for this, I just wrote a basic UART Trojan, which is a small, tiny file that gets put at the very start of Flash. It runs, it takes up the whole memory of Flash, dumps it over UART, and you can extract all the keys. You could also do other attacks, like put something to change the version number or anything, and get basically every single flag using this attack vector. We also tried a couple EMFI attacks, which is electromagnetic fault injection, using this device that sends an electromagnetic pulse into the chip, hopefully timed to skip a certain instruction. The instruction we were aiming to skip was when the debug itself is actually locked. We were not able to skip the instruction, fortunately, but you can see the little pulse in the power line from when we were testing. But the math said we'd have to do something like 10,000 trials to get that to work, so we unfortunately did not have any time. Does anyone have any questions?
All right, thank you guys. So even though we determined that the supply chain attack was out of scope, did your team implement security features to protect against that type of attack if it was allowed?
Yes, we did. One of the very first things that we did as soon as we realized this attack was possible was figure out how to secure ourselves against it. What we came up with doing is most of the logic that sets the JTAG locks, that's actually in the same boot config register, the JTAG locks and the bootstrapping. So we check that when we're setting our JTAG pins, make sure the other pin hasn't been tampered with. And if it does, we'll refuse to boot because someone has touched this before. And then we also, in our firmware binary, or our bootloader binary, when it gets uploaded, we filled all the dead space with zeros instead of nothing, so that if someone preloaded a Trojan, like where firmware is meant to be, we will then overwrite it with zeros. So it takes a little longer to upload, but we're very much secured against this type of attack.
Okay, so those were all the presentations for our teams. This course, the design challenge, was a competition. However, we are going to wait to release the results of that until tomorrow. Tomorrow there'll be an awards presentation for our class specifically. So this is now the end of our virtual presentation. Now if I could have all students in person go back to their tables, and we'll give you guys the opportunity to wander around to tables and ask teams more about their design. But thank you very much to all of our online viewers. Thank you. Right. And please stay at your table until we come around and dismiss you guys for lunch. Okay? Good job, guys. Stay at your table until we come around and dismiss you guys for lunch. Oh, I'm not sure, but someone has gone. So there might be one up there, but someone has. Someone has to know what it is, but I'll see if I can figure it out. Kavi. I just want to say, just remind you guys, so just stick at your table until we come around and dismiss you guys for lunch.
Hi all. Welcome to the Unmanned Aerial Systems Synthetic Aperture Radar course, often referred to as UASR. My name is Jess Durkee, and I'm staff at MIT Lincoln Laboratory, and I will be the lead instructor for the course this year. The main focus of the course is synthetic aperture radar, an imaging technique that utilizes a radar in motion and is often used for environmental mapping or monitoring. Throughout the course, students use the principles of synthetic aperture radar to develop their own functioning system. This system consists of drone hardware they've constructed themselves, the radar unit, and an entire software suite of control code for the radar as well as the signal processing algorithms necessary to turn raw data into a useful image. Students build up these systems piece by piece and use a fly-fix-fly process to debug and improve the performance of their systems throughout the course. The concepts in this course are typically not presented to students until they reach a graduate level or even the workforce, so success and participation in this course demonstrates a technical understanding well above their age. In addition to exposing the students to advanced material, this course is a chance for students to work collaboratively and solve a real-world engineering problem. Today, you will get to see the result of the hard work of these students over the last 4 weeks. We hope you can not only learn from what they will share, but also encourage them to continue to develop and build the skills that will allow them to succeed. Thank you for your time, and welcome again to UASR.
Hello everyone and welcome to our UASR course here at BWSI. This is our radar course we have here, and I will allow our teams, our new radar experts, to introduce you to what they've done this summer.
Hi, I'm Otis Morgan.
My name is Nate Lee.
Hi, I'm Daniel G.
And I'm Ben Vaccaro, and I'd love to talk to you about what radar is. People hear radar and sometimes they think radar, radio, sort of sounds the same. Well, first of all, radar is an acronym. It stands for radio detection and ranging. The ranging is using the feedback you get back by sending a radio wave out to sort of figure out the distance you are from something, the emitter. So it's actually used in all kinds of things in industry, in your lives. You can think about early warning radar systems, autonomous navigation, airport body scanners. You know how they have you step into the thing that spins around, stuff like this. They can also use it for weather imaging to sort of predict what might happen based off clouds and sort of storm formations, but also ground mapping.
So how does ranging work? Well, if you're familiar with sonar, it's a lot like that. The antenna sends a short electromagnetic pulse, which moves at 8 times 10 to the 8th meter, 3 times 10 to the 8th meters per second. And then that pulse will hit a target in the air. That energy will scatter in all directions. Some of that scattered energy will return and be received by the radar antenna. And the whole radar system has a really accurate clock, so it knows exactly when that pulse was sent, exactly when it was received. And by dividing that by 2 to get the one-way travel time, and then multiplying that by the speed of light, you can find the exact range of the object that you're looking at.
So this is the radar equation. It basically tells you the maximum distance that you can detect an object. And if you want more range, you're gonna have to want more transmit power, more receive or transmit gain, which is basically how narrow the energy you are transmitting is. You also want a bigger wavelength and a bigger radar cross section, which is basically the area that the radar will see.
So I'm going to talk about the Doppler shift and how radars can use Doppler shifts to determine an object's velocity. So basically how radar works is that like it receives a frequency, and if an object is moving, the frequency might change, which from that could be interpolated the object's velocity. However, this could only interpolate the radial velocity, which is how close or how far uh, the object is, but not side to side. So you can't really determine the tangential velocity. But basically, Doppler shift is used to determine the velocity of an object.
So talking a little bit about phased array radar. Phased array radars are capable of steering a very narrow beam really quickly through space using phase offsets, and allows for really quick spatial scans, which is really good for target tracking and getting an actual image of where a target is in space. So they're comprised of an array of antenna elements. If each element fires off a signal at the exact same time, then the area at which these signals will constructively interfere would be in a cone directly perpendicular out from the radar. and so this allows you to achieve a beam without using a dish. And then by transmitting from each element a hair later than its neighbor, you can change the angle at which these signals constructively interfere, which lets you point the beam in different directions without actually physically moving anything, which allows you to steer the beam in, I mean, almost instantaneous time instead of physically moving a dish. So that'll be all for the intro to how radar works. So now I'll pass it off to Team 3 for our introduction to SAR. Oh, shoot. Team 2?
No, Team 3. Hi, we're Team 3, and we're going to be talking about radar system components. My name's Joanne.
I'm Iris.
I'm Tim.
I'm Bryce.
And I'm Tharv.
So just to provide like a quick overview of our system, this is our radar system, and we have the radar module, which is a Pulson 452 radar, which is a short-range impulse radar. We also have a Raspberry Pi, and it's connected to the radar. And then we have antennas, which are log periodic antennas, and they're these over here. We have our power supply, which is just a rechargeable USB battery pack, a host computer, which controls the operation, like configures everything and stores our data. And then we have our drone, which is an F550 hexacopter.
Okay, so now we'll talk a bit more about radar. So as Joanne mentioned, we have the Pulson 452, which is a short-range impulse radar. And this basically means it just sends out its pulses as short little bursts of energy. It also has a range resolution of 13.6 centimeters, and this just means that it could differentiate targets that are 13.6 centimeters away from each other. Its operating frequency band is 4 to 4.6 gigahertz, and this makes it an ultra-wideband radar because it has a very large frequency bandwidth. And its maximum power is negative 41 decibel milliwatts per megahertz. And then you can kind of see the radars attached underneath our drone. So I mentioned that the Pulson 452 is an impulse radar, and this means that it transmits all its bandwidth and energy almost instantaneously. And because we want a high range resolution and a high signal to noise ratio to form a coherent image, this means we want a high bandwidth. However, for impulse radars, to transmit an impulse waveform with a high range resolution and SNR, we would need a lot of power, which is an issue. So one solution to this is to transmit a lot of impulse waveforms with lower energy and add many of them together to build a signal. So the signal is coherent in time while the noise is not, which reflects constructive versus destructive interference. And you can kind of see on the bottom, before adding up the low energy waveforms, you can't really see a signal. So the signal to noise ratio is pretty low. But then when you add a lot of them together, you could see a signal kind of emerges.
Okay, so you might be asking, how do we send all these signals and how do we code things and make it connect with the drone? So what we do, you'll hear more about it later, is that we have a drone. Obviously, you'll hear about that from future sections. And what we use is a Raspberry Pi computer, which is kind of a tiny low-cost computer. I think you can buy it for like $30 on Amazon. And what we do is we connect the Raspberry Pi to the radar, so we can actually send our code to the Raspberry Pi, which talks to the radar. Because when the drone is in the air, that also means the radar is in the air because they're too attached. And we need the computer to connect to the radar because it's too far away. And because it's too far away, we need a computer that is close to the radar, so we use a local computer, which is the Raspberry Pi. And on our host computer, where we do all of our coding and we send all of our signals to the Raspberry Pi, we use GitHub, which lets us open repositories and code. And then we use VS Code, which is a host just to have all of our code. And we send all of these files, all of these code to Raspberry Pi so we can run it, get back signals, and get back projections and things that you'll hear about later. Thank you.
Okay, the antennas. For our project, we use something called log periodic antennas. It's called this because its electrical properties repeat periodically as a log of the frequency. These antennas, they kind of look like little green Christmas trees. You'll see it on the slide. And they have a couple important things that help us do our project. First, they're directional antennas, which are made to operate over a wide frequency. This frequency is from around 2 gigahertz to 11 gigahertz. And using this, they can have a gain of around 5 dBi, which isn't phenomenal, but for our project, it'll do. And lastly, they have a dipole-like radiation pattern, which looks like a donut coming off of the tip of it.
Okay, so the actual drone that we're flying is an F-550 hexacopter with Q in-out motors. So basically the radar, as you can see, is attached to the bottom of the drone. We use zip ties in our case to attach it, and we also had it angled a bit downwards so that when we're flying overhead, we can get good angle of the scene. And the scanning from above also gives different angles and will improve the image quality. As you saw with sometimes with walking SAR, where we were just walking and holding the radar, we sometimes got a little bit more blurriness or not as good image quality. In our case with our drone, we did have some issues. Our feet actually broke early on in like the first week of the program, but we were able to get around that, and we duct taped the feet, and we were able to make it work. And the feet didn't really affect too much the landing or things like that, and our pilot was able to still land well. We also had issues where our drone was automatically kind of leaning backwards and to the right a little bit from takeoff, but our pilot was also able to adjust to that, and we were able to kind of fix that issue and still get good scans and good data. So as far as the drone hardware, we're using X9D transmitter and an X8R receiver, as well as radio telemetry. I don't know if you could see on this, maybe on the drone over there, but we have also a GPS, which we don't really use as much though, because we're not really going over a very far or large area. And as far as our power, we use a lithium polymer battery or LiPo battery. And in terms of software, we use something called Q ground control, which connects to the drone, as Atharv talked about, from the computer and is able to calibrate from there and then arm the drone to be able to fly. And we're also able to control and set certain parameters from there, from the ground with Q ground control, such as auto altitude like hold. And we also use mocap or mocapture, a motion capture, which uses IR illumination and sensing. So we have these small mocap balls, 3 of them attached to the radar, so that we can see where the radar is in time, like actively see it live and kind of track its motion. And we use that in our calculation for back projection and other things like that. And I'll pass it off now to Team 5. Thank you.
Hello everyone, we are Team 5 from the SAR course, and we are giving a brief introduction to the synthetic aperture radar. I'm Celestine.
I'm Varisha.
I'm Tyler.
And I'm Rishi.
So now we'll start talking about what synthetic aperture radar is. So traditional radar is limited by antenna length because in order to get a better resolution image, the antenna length must be longer. So as you can see, the 20 centimeter resolution image is a lot more clear than the 1 meter resolution image. However, the antenna needed for that 20 centimeter resolution is a lot longer, and it's impractical to attach such a large antenna onto a moving platform. However, that's where synthetic aperture radar becomes useful. Next. So synthetic aperture radar, or SAR, utilizes a moving platform to create a synthetic antenna, which removes the need for such a long antenna. And it does this by combining the radar pulses from the different scan positions into one data set, which allows us to get a better resolution image. However, what's important to note that the SAR image assumes that nothing is moving during the data collection and scanning phase.
Nice. As said earlier, SAR assumes that everything is still. And this is a large issue because it comes from something called Doppler shift. Doppler shift is when an object is moving towards or away from the radar platform, which changes the frequency of the returned signal. This can often be heard in more auditory effects, such as fire trucks, ambulances, or police cars, and how when they're coming towards you, the pitch shifts upwards, and when they're coming away from you, the pitch shifts downwards. And when this occurs in SAR, it's a visual bug which makes an object have motion blur or smear, which disallows you from seeing pretty much anything like about the object or even its size, and just pretty much ruins the image. Next. So I'm just going to talk about the steps of SAR. The first step is, of course, mounting the radar onto your moving platform sideways, so you can get the proper target area. The next is making sure that the pulse waves are hitting the ground and reflecting back from your objects. And after that, the radar receiver actually detects the reflected signals and finds each individual pulse's strength. Next, this process just continues on and on until the scans are finished, and the radar just continuously sends these waves out. And for the final step, the radar itself has a program which combines all of this signal data into one data set, which simulates the resolution of a much larger antenna or much larger aperture.
Okay, so moving on to a little bit more about the resolution. So resolution is essentially how clear we can see the image, and a smaller resolution obviously means we can see the image a lot better. So if we look at the one on the right side, we have a 20 centimeter resolution, which is much clearer than the one on the left, which is showing a 1 meter resolution. And likewise on the bottom, we can see the one on the right side has a 4-inch resolution, whereas the one on the left side has a 12-inch resolution. And obviously, a smaller resolution allows us to see the image a lot clearer, but it has a much larger integration time, and so we have to be looking at the area for a lot longer. And now we're going to do a quick comparison between synthetic aperture radar and optical. So each of them has its own use cases, which are vastly different and like very different capabilities. So synthetic aperture radar can look past mediums like walls and stuff, and it's not limited by the weather. So likewise, it doesn't come in color, but it uses microwave pulses to detect objects. On the other hand, we have optical. Optical shows all things that we can see, and it's in color, and it uses reflected light waves. So if we look at the right side, we have an optical image of a car, and looking at that, we can only see the top view. But if we look at the left side, we have the synthetic aperture radar view of it, and so we can look past the object and we can see the frame of the car underneath. And on the bottom, we can see the topmost image with the clouds is the optical one, and we can't see past the clouds, although there's many buildings below, and we can see all those buildings in the synthetic aperture radar one, and it's visible.
After we see the differences between the optical image and the scan image, I'm going to introduce two SAR scanning modes. There are two modes. One is spotlight mode. The spotlight mode focusing on one single target and area for radar, and the radar angle changes as the platform moves. The feature is this scan mode scans for specific spots and it focuses on the spot, so it has a higher resolution to get a better image. The another mode is a strip back mode. The radar angle stays the same as it scans as a continuous area while the platform moves. This mode provides a larger scan area, but the resolution is lower. After we collect the scan data, we use back projection algorithm to generate image using processed SAR data. It has no limitation but requires a lot of computation. Better resolutions require more integration time. SAR assumes nothing is moving, so moving objects such as cars and people will appear as blurs in the image. It is useful for detection and classification because we can also detect stuff that are covered. And there's an image of the space SAR when we're scanning the Great Boston area. Thank you. Now we are moving on to Team 4 to introduce the mocap system and the radar system. Thank you.
Hi, this is Team 4. This is Jason, Joseph, Sophia, and Daniela. We're going to be talking about the drone and motion capture system we use for our SAR. Okay, so there's a lot of parts on this screen right now, so I'm only going to gloss over a little. We basically have it split into a bunch of air components and also ground components. Ground is mostly for control, while air is, the drone and everything that makes it move. We also have some lines talking about how it communicates. For example, this transceiver connects to that receiver, and we have two telemetry units that talk to each other. And yeah, that's basically it. Okay, so first, this is our drone model. It's an F550. It's a hexacopter drone, meaning it has 6 propellers, 6 legs. If you look here, each propeller, the propellers alternate between clockwise and counterclockwise turning, so that's pretty cool. It helps, for thrust. Yeah. This is our Pixhawk flight controller. Basically, this is the brain of the drone. It controls how much power goes to each motor, which helps us choose if we want to go up, down, left, right. It controls all that. It also includes many important sensors like our accelerometer, our compass, our gyroscope, our barometer, and those help us, control altitude, control speed, all that stuff. And everything else that for communications also plugged into this. So, yeah, it's basically the brain. And this is our drone frame. It's a Hexa Plus. Basically, all the guts of the drone go in here, all the wiring, etc. All stays protected inside of this frame.
going further into the first of our two communication system for our drone, another critical component, the first ground component that we'll talk about more in depth is our transmitter. If the flight controller can be thought of as a motherboard, the transmitter is kind of like a keyboard. So when you press a key, obviously, your computer's on your computer, for example, your computer's motherboard processes it and it reacts in the way it's programmed to. In the same way, on a transmitter like the Tyrannus that we used here, we're able to program different switches and different motions to mean different things. On our transmitter specifically, for example, moving this left stick here up or down causes our drone to fly up and down respectively because it's equal to adjusting the amount of thrust that the drone is producing, so how hard the motors are spinning. Up and down motion on this right stick here is analogous to kind of making the drone tilt forward or back. It's changing the attitude or the pitch of the drone to allow us to move forward and back. And since we didn't really need roll, our left and right motion, left and right motion on the right stick causes the drone to kind of turn left or right. It changes the attitude, so the way it's facing, essentially, to allow us to make turns, essentially. Other than that, some other small important switches that we use, other than the buttons, we also, other than like the buttons to turn on the Tyrannus and to switch between pairing modes, we also have our assigned arm/kill switch. It's back here, and it allows us to turn on our drone to make our drone start receiving input from the transmitter when we're ready to fly, essentially. And then if we're in a crash, if we're close to crashing, or if we're in a situation where we're no longer able to control the drone, we can just flick it back down and it'll kill the drone, cause it to just lose all input and fall, essentially. Thankfully it's on a net, as you can see over there. Other than that, we also have our flight mode switch, which allows us to switch between the different, I guess, configurations of the drone. Tell it to either fly freely in stabilized mode, mostly freely, of course being auto stabilized, or stay at one given altitude, so you don't have to use the left stick in altitude hold mode. Next slide, please. The other end of this kind of communication system is our receiver. Our specific one was an FrSky X8R. I'm not sure if you know what that is, but essentially all it does is it takes the inputs from the transmitter. It just gets them and sends them over to the flight controller for interpreting. Next slide, please. The other set of communication systems are two telemetry modules. So there's one, the ground one that connects to our computer, and then the onboard one that is connected to our flight control on the drone. These two they facilitate, they allow us to communicate with our drone via our laptop and the software we use, which is called Q Ground Control, which we'll discuss in a bit. So essentially, they just think of them like a pair of walkie-talkies. They're essentially just sending over like any parameters we set within Q Ground Control, like status messages, so that we're able to essentially interface with our drone through Q Ground Control. Next slide, please. Other than that, kind of getting into more onboard components now, we also have our electronic speed controllers. All these do is essentially, as the name suggests, regulate the speed at which the motors move. They're connected directly to the flight controller. They're kind of between the flight controller and the motors. So when the flight controller, in response to input, tells the motors to spin with a certain velocity, the electronic speed controllers make sure that they're spinning at the right velocity and they're not spinning too hard, so the motors don't overheat and get fried. Next slide, please. And then kind of our last major components, pretty self-explanatory, are our motors and our propellers. As you can probably tell, the motors pretty much just rotate at a certain angular velocity in response to the inputs by the flight controller, to allow the drone to fly and to fly in different directions depending on how much thrust each motor is producing. And then the propellers, we use 10-inch carbon fiber propellers, are just their profiles, they have an airfoil shape, and they enable the drone to fly by essentially increasing the amount of thrust that the drone is producing. Not mentioned here are also the hardware safety switch and battery. They have pretty small roles. The hardware safety switch is just there so we can press it when we're ready to fly, and when we're not ready to fly, the motors don't start spinning and like cut up our hands. And then the battery is just there to, it was a 4-cell battery, and it's just there to power all of our components
and allow us to operate our drone. Now we'll be going on to Q ground control.
All right, so this is the software part of the drone, which is called the Q ground control. And what we're able to do is if we plug in the telemetry on the laptop and on the drone, we're able to connect our laptop to the drone so that we can set up settings and calibrate our drone effectively. And as you can see here, it's right now it says disconnected, but when everything is connected from the laptop to the drone, it will say ready, which basically gives us the green light to start flying. But before we start flying, we also need to calibrate our drone and these include the accelerometer, the compass, and the gyroscope. And what the accelerometer does is that it prevents the drone from drifting in directions. And as you can see in that picture over there, those are like the steps we have to do to calibrate our accelerometer. And the compass, what it does is that it basically corrects our sensor errors in the drone so that also, again, it doesn't really drift in places that we don't want to. And the gyroscope, again, it also helps the drone stay steady in the air. So then, yeah, so that we don't have any unwanted crashes into the net or into people.
All right, so in order to track our position for the drone, we need to use a mocap system. So basically, usually, drones would use an IMU to track their location internally, but since we don't have a good one, we need cameras to help us do that. So basically, as you see here, we have these mocap cameras that capture reflections off of the, off the mocap markers. And from this system that is pictured in the third image, we can start and stop recording whenever we want in order to capture the location, and it gets exported into a CSV file as shown here. So this CSV file returns the X, Y, and Z positions of the drone at different times. So we could then use this data to sync it up with our scan data in order to produce a working image.
And then now we'll go into team 2 for image formation.
Hello, this is Team 2, and we're going to talk about image formation. So, my name is Melis.
I'm a truth.
I'm a teacher.
And I'm Max.
So far you learned how we collect the data and the drone systems, and now we're going to talk about how we use this data to make images. So we get the data as a bin file. That is just the type of the file we get it at. And then we use a 2D array system to basically get this data and make it points so we can graph it. And then we have range, time, intensity, shortened for RTI plots. If we get the intensity from the bin files, we can generate a really raw RTI plot, which does not have any filtering on it. While that is simple-ish, it is not ideal because there's a lot of external factors that can interfere with our clarity, like noise and clutter. In order to overcome this, we can apply filters, one of them being intensity filters. The way we calculate this is we calculate the mean intensity, so the average intensity, and then we subtract this from the intensity we get from the radar data. And as a result, we get a more clean image. So as you can see in the rightmost corner down, this scenario represents the radar being stationary, this thing here, and then this corner reflector being rocked back and forth in a slow motion. And in the image, you can see that there's an outline, like a dark blue outline of the motion we did. So this is like how the simple way works. And in the next few slides, we're going to explain more complex processes we apply.
Yeah, so for our RTI plots, we plotted range on the x-axis, slow time on the y, and with intensity, with darker regions being regions of more intense activity from the radar. So initially when we did this, our RTI plots had a lot of clutter, meaning it was difficult to identify the reflector that we were trying to find. So what we did is we applied motion filters, and we were able to eventually get a much more clear image of the reflector, as you can see in the top right. And using that, we also actually developed it into a live RTI system, which can take raw radar data and make it into an RTI plot that appears at the top of the page while filtering out old data at the bottom. That can actually allow you to see real-time movements of reflectors. And you can see that in the video in the bottom left. And after that, we developed it into a time and range alignment system, which we can do automatically or manually, where we align the mocap system that you learned about earlier with the radar data to ensure that the reflectors are positioned in the correct spots for both systems.
So now on to actual back projection. So I like to think of this as the big brother to RTI plots. Back projection is basically how we're supposed to take these radar images and turn it into actual 3D maps that we can detect what items are inside of it. So it starts off the same as RTI, where we take the radar but also the motion capture files and convert them from 1D arrays over to 2D arrays. But after that, there's a process called time alignment. That involves taking each frame of the radar and lining it up with one frame of the mocap. Since the radar and the mocap are both independent systems, they can't easily be lined up one to one. So what we do is that we take the closest motion capture frame from each radar frame, and if a radar frame is not close to any sort of mocap frame, we just eliminate it. We do this for every single frame within our datasheet until we get timeline data. After that, we're able to apply intensities to these plots and find the distances to every single pixel in respect to the drone to create a 1D graph. That's called a scan. After that, we can do this for every single scan that we have, usually spanning from around 600 and 700, and then we compile them all into like a main matrix. And as you can see here, the main matrix has one singular point where we detect a can. That is the point where, out of all the radar scans that we have, that point is where a lot of distance was the most intense. And after doing that, we're able to detect exactly where an object is with only a radar that only detects distance. And on to the right, you can see a synthetic aperture or synthetic back projection that we were able to get of a space shuttle, which was one of the tests that we tried to do when we were practicing.
Okay. Now, this is the back projection equation. I know it looks a little scary, but it's okay. I'm going to break it down. So basically, it describes the radar measurement that back projection is trying to undo. So first off, on the left side, Z of R of N is a complex value in the radar range profile, where R is the range variable and N is the pulse index. And because the drone is moving while it scans data, that value is always going to change. The integral means that it receives signal contributions from every single possible point P in the scene. P represents a point in space, and the dP at the end of the equation tells us that all these spatial contributions are being added up together. And then A of P of N is the radar reaching that point during the scan. And then S of P is the complex reflectivity of whatever is at the location. So a metal reflector will give off a strong value, while if there was nothing there, it would give off no value at all. R of P is the distance from the radar during scan N to point P. The exponential term describes the phase caused by that travel distance. J is an imaginary number, and then C is the speed of light, and then F is the frequency, which depends on how fast the phase changes. And then it's 4 pi instead of 2 pi because the wave has to travel to the target and then back to the radar. And then the expression R minus R compares the range band we are examining with the range where that point should appear. So if a target is really there, then the signal should line up and reinforce each other. But if it wasn't, the phases don't line up, so a lot of the energy cancels out. And that is how curved range measurements become a focus point in the final image. So this is a timeline of our back projection. We first started with a simulated 5-point scatter where we could test the image formation without dealing with issues of time alignment. And when those measurements were projected back into space, they focused back into their original locations. We then moved on to the marathon image where we can see Mr. Einstein right there. And so it tested whether the same method could recover a distributed scene instead of a few isolated targets. It also exposed coordinate problems immediately because if we messed up our coordinates, the image would be like distorted, flipped, rotated, all that weird stuff. And producing a recognizable marathon image showed that the algorithm could preserve the structure of a larger scene. After that, we moved to the best part, the drone scan. Are you guys ready? It's a 6-7. This was the real complication started because the radar motion capture system recorded on separate clocks. So we had to manually create an RTI and then have to do time offset and range offset. And then we have to adjust it until the predicted tracks sit directly on top of the strong reflector tracks. And not yet. Once the recordings were aligned, the motion capture positions are interpolated at the exact time of each radar scan. This means every radar measurement is paired with the position where the drone was actually located when it was scanned. And the radar traces are converted into a complex signal, and background energy is reduced. The carrier phase is handled using the 4.3 gigahertz center frequency. For every image pixel, the program calculates the full distance from the drone to that ground location. It samples the matching radar range, and after the phase correction is applied, that value is accumulated into an image. We also generated several reconstructions of the same back projection because even small changes in the time offset and range offset could blur the cans in the image a lot. So our best solution was to run 10 at the same time, but in return, that took a lot of time. The black X marks on the 6-7 shows reflector peaks. So it's kind of like
lighthouses where it shows the calibration, and then the stuff in the middle is the actual cans that were in between the reflectors, showing the beautiful 67. The drone pad. Oh, the final stage is a 3D visualization on the right, and it comes from the same reconstruction, but the program saves snapshots with more radar scans are accumulated, so then the image gradually rises into focus. And then the drone path is shown beside the surface, which connects the movement of the radar to the target locations. The 3D view lets us see the final result while also understanding how that result formed over time. Instead of only seeing the final image, we can watch the measurements from the moving radar and drone gradually reinforce the correct locations in the scene. And this is a summary that shows the back projection results of all the teams that you've been listening to. The images look different because each team made its own choices on how they go about back projection, but in the end, every result uses radar motion to place measured energy back into physical space. And in the end, we all got the image. So thank you for listening to our presentation. 6-7.
Right. Thank you, and a huge congratulations to all of our teams here at BWorks this summer. We had a great time, clear success this summer, and also I will now pass this over to the Syracuse team. We had one team visiting us from Syracuse this summer, also participating in the UASR course. So I will let them introduce themselves.
Hi, we're the team from Syracuse University. My name is Lila Temis.
My name is Priya Pavor.
I'm Elias Mannion.
So jumping right into an introduction to radar. Radar, for anyone who doesn't know, stands for radio detection and ranging. It's a process that sends out electromagnetic waves and uses the received echo to determine the time and position of some target. And the ultimate goal of most radar systems is to capture an image that you couldn't get through an optical view. And a standard radar system has a couple main components: a transmitter, antenna, duplexer, and receiver. And then the duplexer is what switches between transmission and reception so that what you're receiving isn't just the wave that you're transmitting. Okay. So the system that we're using is synthetic aperture radar, and it compared to standard radar, the main difference is that it can use a much smaller antenna to get a similar image. Like traditional radar, it's transmitting microwave pulses and recording received echoes, but it kind of differs in transmission and reception, which is something we'll go into a little bit more later. Okay. So technically speaking, there isn't a better between traditional radar and synthetic aperture radar, but within our constraints, mostly the drone's weight capacity and also just size, what we can fit on the drone, synthetic aperture radar is better. There are traditional radar systems that can be put on moving platforms, but they are rarer, and whenever a radar is on a moving platform, it has to account for something called the Doppler shift. And SAR is special because it has to account for, because it requires motion, it has to account for the Doppler shift both in terms of if the target is moving, but also always in terms of when the radar is moving in relation to the target. SAR also, some of the limitations of synthetic aperture radar is that it involves processing delays, whereas traditional radar can get a real-time image. This is because SAR has to cross-reference data from a motion capture system and data from the radar itself, whereas traditional radar is just using the information from the radar. There are some advanced avionic computers that fit on drones, but those are expensive and heavy, and they can process the data that the radar is getting well in the air. But because we're using a Pulson 440 and we don't have the computational capacity on our drone to process the data, we have to wait till the drone lands. Okay. We're going to go quickly into frequency and Doppler shift. Radar frequency is the weight at which an electromagnetic wave oscillates per second, which is wavelength. SAR and traditional radar do not differ in the fact that they, in electromagnetic frequencies, they both use frequencies from 3 megahertz to 300 gigahertz. But traditional radar uses the Doppler shift to determine if the target is moving. And that can be used to determine what kind of target you're looking at. For example, in air traffic control, traditional radar can use the Doppler shift to determine how fast an object's moving. And that allows it to distinguish between like a bird and a plane. But in SAR, the Doppler shift comes from the movement of the radar itself. Okay. Going over some quick applications. Different applications of SAR require different frequencies to attain the image with the proper level of detail and focus. For example, when you're urban mapping with SAR, you use high frequency waves, which offer fine detail, but it doesn't penetrate things like plant canopies. Whereas when you're using large scale geological or tectonic deformations, when you're trying to map that, you need to be able to penetrate thick surfaces like a really thick layer of dirt to be able to see underlying ground structures. So you use low frequency or long wavelength.
Our drone and radar system, the drone we utilize is the Holybro X650, which is a different drone than from what the other teams were using, as Lila said, with the issues from before. So we had some issues with building it. So we started with like a motor. We had issues with the drone and how it was flying. And then the software we use is called Archie Pilot, which helped connect and fly the drone so we could test flights in software so we knew it could fly. And then the propulsion system is just stuff we use to quick assemble and the carbon fiber arms. And the drone flew faster, which might have also messed with our data because it was pulling the antennas down. Yeah. And then the radar, we already went over what it does. And it connects to a Raspberry Pi, which then shows the code for us to actually use the data collection and back projection.
Okay, now I'm going to talk a little bit about the data collection process. So SAR transmits continuous microwave pulses and to the ground, and it records the backscatter, and backscatter is just the echoes that are reflected. So computers later use signal processing in order to combine many echoes, which is what simulates the effect of having a giant antenna with having a much smaller antenna system. And that's what allows us to have highly detailed image resolution. SAR mainly records two components of the wave that returns, phase and amplitude measurement. So phase is tracking the distance that the wave is traveling, and amplitude shows the roughness of a surface. And SAR collects raw data, which is processed through algorithms, and this processing is what converts the raw image into a coherent image. So for us, we had a couple steps that we had to do in order to collect data. So the radar itself is transmitting a frequency modulated microwave pulse, which is called a chirp. And then the echo is reflecting off the target. Afterwards, the receiver is storing four things: amplitude, phase, timestamp, and drone position. As said before, amplitude and phase are recorded from the radar system itself. However, we had to use something called a motion capture system in order to record the timestamp and the drone position. And then we're repeating this thousands of times. So for our walking test, I think we got around 1,500 pulses per test. And then when the drone was in air, we got around 1,000. And that's how we're compiling our raw SAR data set, by doing this over and over and over. But we still need to form an image even after we do all of this. This is what we use back projection for. So back projection is simply post processing, and it's using the raw data to construct an image pixel by pixel. Each radar pulse records the amount of time it takes to receive an echo, and that's categorized into different range profiles. So back projection is projecting the radar's time delayed echo data backwards across an imaging grid, and for every pixel it determines how far from the radar's position the pixel itself is and adds up the matching return signals to create an image. So we did have a few problems throughout this process. So the first one is we had a different drone and propulsion system than last year. You can tell that from the MIT teams, a lot of them were using hexacopters, which just means a drone that has 6 arms. Ours is a quadcopter, which has 4. And so we had to use the MIT team's hexacopter building sets. However, we had to figure out where things went on our quadcopter. And we also were having problems with things like the motors burning out, and the fact that Syracuse University does not have a mocap system right now. It's still being installed. And so the first time we used motion capture data was when we came to to MIT to do the competition.
We also had a couple software issues. So all the MIT teams are working off of wireless LAN networks or wireless LAN. But our wireless LAN stopped working because the IP address of the Ethernet port changed somehow. So we had to run our drone completely on local networks, hotspots, which meant that every single time we connected to the Pi, we had to figure out the new IP for the network that we were trying to use. So before I go into results, I want to quickly describe. I'm sure other teams have, but what we're trying to do is capture an image of a series of cans that are laid out in some configuration under a tarp, which means that our waves have to penetrate that first surface and bounce off of the cans. So ultimately, what we figured out is there was no issue with our back projection code. We ran it on data from last year, and we got the correct image, and we ran it on data from this year. However, there was an issue with our data collection code. That ultimately stems from the pulse indication index. So we were sending out 500 pulses per second. We should have been sending out somewhere near 2,000 or 3,000. And that means that our data is it's gonna be blurrier, so we weren't able to determine the image, and we didn't have time to necessarily configure the image that we did get by changing the resolution or the X and Y ranges, because we didn't realize we did have what we were looking for in our data set. Additionally, so this issue stemmed from not having a motion capture system. We were running all of our tests off of motion capture data from MIT, but that was kind of unrelated to the data that our radar was actually receiving. So when we were doing our tests, we attributed issues to the fact that our motion capture data wouldn't line up with our real radar data because it wasn't motion capture data for that data test. So when we got here, we were able to run our first test with actual motion capture data and our raw radar data at the same time, and that's when we figured out that we were having this issue went further than that. But we did ultimately get an image. If we had more time, we'd be able to fix the resolution issues. But yeah, that's everything. Yeah, thank you so much for MIT for this opportunity and Professor Graham at Syracuse University, who helped us understand radar systems. Yeah, thank you.
Thank you.
Thank you.
Oh, thank you, Connor. Yeah. Thank you to our TAs.
Yeah.
Okay.
That's off. Where I get this?
Do you want the microphone back?
Thank you so much.
No, thank
That's
you.
right.
Appreciate it. You're welcome. Oh no, just going over to Kevin. Appreciate it. Thank you.